Welcome! Today we are going to explore Quivers, also known as directed multigraphs. And I want you to hear that word without any fear attached to it, because a quiver is actually a very simple and very beautiful idea. It is just a collection of dots connected by arrows, but those arrows have a direction, and that direction matters. By the end of our time together, you will see that a quiver is really just a gentle first step towards something deeper in mathematics called category theory. But we are not rushing there. We are going to take it slowly, one idea at a time. So let us begin at the very beginning. Start with dots. Every quiver starts with points. Just points, nothing more than that at first. We give these points a name. We can call them vertices. Some people prefer to call them nodes. In the language of category theory, you will sometimes hear them called objects. But for now, no matter what name we use, the idea is the same. They are just named locations. Places that exist, sitting quietly, waiting to be connected. In our first picture, we have three such points. One is labeled A, one is labeled B, and one is labeled C. That is it. Three named places. No connections yet, no arrows yet, just three dots, and their names. And I want you to sit with that for a moment, because even this simple picture is already telling you something, that in mathematics, we often begin by naming the things we care about before we say anything about how they relate to each other. So here is your first question to think about. Looking at those 3 points, A, B, and C, how many vertices do you see? The answer, of course, is 3. But the habit of pausing and counting carefully is one we want to build right from the start. Add one directed arrow. Now we are going to add something new. We are going to draw an arrow. An arrow in a quiver goes from one vertex to another. It has a starting point and a finishing point. We call the starting point the source of the arrow, and we call the finishing point the target of the arrow. Let us look at a concrete example. We draw an arrow. Let us call it simply the arrow A, and it goes from the vertex A to the vertex B. We can write this as A goes from A to B. The arrow starts at A and it ends at B. Now, associated with this arrow, we record 2 pieces of information. The source of A is A. We write that as source of A equals A. And the target of A is B. We write that as target of A equals B. In the picture, you see the 2 dots, A on the left and B on the right, and a single arrow drawn between them, pointing from A toward B, and the arrow is labeled A. That label is important. Arrows in a quiver have names, just like vertices do. The arrow is not anonymous. It is a specific, named piece of data. This is the heart of what a quiver is. Named places, and named connections between them, where every connection knows where it starts and where it ends. Direction matters. Now here is something I really want you to absorb, because it is one of those ideas that seems simple but turns out to be genuinely important. In a quiver, the direction of an arrow is part of the mathematics. It is not decoration. It is not a detail you can ignore. The direction is data. Let me show you what I mean. Suppose we have 2 vertices again, A and B. In our first picture, we draw an arrow from A to B. That arrow is labeled A. It points from A toward B. In our second picture, we draw an arrow from B to A. That arrow is labeled B. It points from B toward A. These are 2 completely different pictures. They are 2 completely different pieces of mathematical information. Even though both arrows involve the same 2 vertices, A and B, they are not the same arrow, not even close, because one goes one way and the other goes the opposite way. A quiver is what we call a directed structure. Every arrow has a definite direction built into it. And when we study paths through a quiver, or when we eventually build categories from quivers, that direction will govern everything. You can only travel along an arrow in the direction it points. You cannot simply reverse it whenever it is convenient. So remember, in a quiver, an arrow from A to B and an arrow from B to A are genuinely different. The direction is always part of the story. Multiple arrows are allowed. Here is a feature of quivers that sometimes surprises people at first, and then quickly starts to feel very natural. In a quiver, you are allowed to have more than one arrow between the same 2 vertices. Let us look at an example. Suppose we have our vertices A and B again. We draw one arrow from A to B, and we call it A. Then we draw a second arrow, also from A to B, and we call it B. Both arrows start at A, and both arrows end at B. Their source is A, and their target is B in both cases. And yet, A and B are different arrows. They are not the same. Even though they share the same source and the same target, they are distinct, named arrows. They are different pieces of data in the quiver. This is why a quiver is described as a directed multigraph. The word multi here is doing exactly the work you might expect. It signals that multiple arrows between the same pair of vertices are perfectly allowed. There is no rule that says you can only have one connection between 2 points. In the picture, you see A on the left and B on the right, and 2 separate arrows drawn between them, one labeled A and one labeled B, both pointing from A to B but clearly drawn as 2 distinct arrows. This might feel a little abstract right now, but it becomes very natural once you start seeing real examples. And when we eventually build categories from Quivers, having multiple arrows between the same 2 vertices will correspond to having multiple different ways to go from one object to another, which happens all the time in mathematics. Loops are allowed too. We have seen that a quiver can have multiple arrows between the same 2 vertices. Now I want to show you one more thing that a quiver permits. Something that might feel a little unusual at first, but is completely natural once you sit with it. A quiver can have a loop. Look at the picture. We have vertex A on one side and vertex B on the other. There is an arrow from A to B, labeled A. We have seen that before. But now look carefully at vertex B. There is a small curved arrow sitting right there at B. It leaves B, curves around, and comes back to B. That arrow is labeled L. That is a loop. An arrow whose source and target are the same vertex. In precise terms, the source of L is B, and the target of L is also B. The arrow begins at B, and it ends at B. It goes nowhere else. Now you might wonder, what is the point of an arrow that just goes back to where it started? That is a fair question, but I want to encourage you to hold that question gently, rather than letting it become a reason to dismiss the idea. In mathematics, loops appear naturally and meaningfully in many situations. They can represent a process that cycles back to its starting state, or a transformation that maps something to itself. Later, when we talk about categories, loops will correspond to something called endomorphisms, maps from an object back to itself, and those turn out to be extremely important. For now, just take note. Loops are allowed. They are not mistakes. They are a genuine and legitimate feature of a quiver. A quiver is data, not just a picture. We have been drawing pictures, dots and arrows, and pictures are wonderful for building intuition. But I want to pause here and say something more careful, because in mathematics, we always want to know precisely what kind of object we are dealing with. A quiver is not just a picture. A quiver is a specific, structured collection of data. And that data has exactly 4 ingredients. The first ingredient is a set of vertices. We give this set the name Q0. It is simply the collection of all the points in our quiver, every named location. The second ingredient is a set of arrows. We give this set the name Q1. It is the collection of every named arrow in the quiver. The third ingredient is a source map. We call it S. It is a function that takes any arrow from Q1 and returns its starting vertex, a vertex in Q0. So S is a function from Q1 to Q0. You hand it an arrow, and it tells you exactly where that arrow begins. The fourth ingredient is a target map. We call it T. It is also a function from Q1 to Q0. You hand it an arrow, and it tells you exactly where that arrow ends. In the diagram, you can see Q0 on one side and Q1 on the other, with the 2 functions S and T drawn as arrows going from Q1 into Q0, the source map and the target map, each doing its job. These 4 things together, Q0, Q1, S, and T, completely and precisely describe any quiver you could ever draw. Every vertex, every arrow, every direction, all of it is captured. Nothing is left to interpretation. And this matters because it means a quiver is something you can reason about algebraically, not just something you can sketch on a piece of paper. The picture is a guide. The data is the mathematics. First full example. Let us now read a complete quiver, carefully and thoroughly from start to finish. Here is our quiver. We have 3 vertices, A, B, and C. And we have 5 arrows, A, B, C, D, and L. Let us record the source and target of each arrow, one by one. Arrow A goes from A to B, its source is A, and its target is B. Arrow B also goes from A to B. Its source is A, and its target is B. So A and B are 2 distinct arrows that share exactly the same source and the same target. This is the multiple arrows feature we discussed, and here it is, appearing concretely. Arrow C goes from B to A. Its source is B, and its target is A. Notice carefully. C travels in the opposite direction to A and B. Even though it involves the same 2 vertices, it goes the other way. Direction matters, and C is genuinely different from both A and B. Arrow D goes from B to C, its source is B, and its target is C. Arrow L is a loop at B. Its source is B, and its target is B. It leaves B and returns to B. Now let us write this out as formal data. The set Q0, our vertex set, is the set containing A, B, and C. The set Q1, our arrow set, is the set containing A, B, C, D, and L. And the source and target of each arrow are precisely as we have just read them. Every arrow accounted for, every direction recorded. This is what it looks like to fully unpack a quiver. Take your time reading through the table. There is a lot of small, precise information here, and getting comfortable reading it carefully is exactly the skill we are building. Guided questions for reading a quiver. Now it is your turn to practice. I am going to give you a quiver to read on your own, and I want you to genuinely pause and think through each question before moving forward. This is not a test. It is an exercise in building the habit of reading a quiver carefully and systematically. The quiver has 3 vertices, A, B, and C. It has arrows labeled A, B, C, and L. Look at the picture, trace each arrow, identify its source and its target, and then use that information to answer the following questions. First question, how many vertices are there in this quiver? Count them. Second question, how many arrows are there? Count every single one. Do not forget the loop. Third question, which arrows have A as their source? In other words, which arrows start at the vertex A? Fourth question, which arrows have C as their target? In other words, which arrows finish at the vertex C? Fifth question, which arrow is a loop? I want you to really stop here. Do not just read the questions and move on. Pick up a pencil if you have one. Trace the arrows in the picture. Write down the source and target of each arrow, and then answer each question from what you have written. The questions themselves are not difficult, but the practice of reading carefully, tracing each arrow, identifying its direction, distinguishing sources from targets, is a habit that will carry you a long way as we move forward into deeper mathematics. Build that habit now, while the structure is simple.